right, so here is another application problem of sinusoidal functions that I want to go over with you. It's the bouncing spring problem. It says a weight attached to the end of a long spring is bouncing up and down. As it bounces, its distance from the floor varies sinusoidally with time. Okay, so in other words, it's going up and down. But time is passing. That's why the x is moving. So basically it's up and down, except time is passing, so it's going up and down, and that's why we call it sinusoidal. All right, so again, we have time is our x value, and its height is our y value. Okay? So this particular situation says, as it bounces, you start a stopwatch. When the stopwatch reads 0.3 seconds, the weight first reaches a high point 60 centimeters above the floor. And because of where this is, I'm going to just change my axes a little bit and draw the world's worst vertical line in the process, but hey, that's how life goes. So it's, again, you start a stopwatch. When the stopwatch reads 0.3 seconds, the weight first reaches a high point. So at 0.3 seconds, we are at a high point. So this is my high. And it says 60 centimeters above the floor. So this is at 60. Then it says the next low point, which is 40 centimeters above the floor, occurs at 1.8 seconds. You know what? I just can't do it, folks. Sorry. This is too not vertical. Try again. There we go. I'm happier now. Okay, so 0.3 was up here at the high of 60. Ironically, I think it looks a little bit more angled in the camera now, but that's okay. And then the low was at 40. I'm just going to go ahead and put it right here. And that happens at 1.8 seconds. So high here, low here. Well, first of all, I need to go ahead and figure out what that tells me about the rest of the whole situation. It tells me it goes back up, and however long it took to get from here to here, that's how long it's going to take to get from here to here. So 1.8 minus 0.3, think about 18 minus 3. That's 15, or 1.5. So 1.5 here, 1.8 plus 1.5, 18 plus 15 is 33. This is 3.3. Okay, so my whole period, 3.3 minus 0.3 is just 3 seconds. It takes 3 seconds to go all the way back down and back up to where it came from. All right, sketch a graph of the sinusoidal function. I sure have. I haven't put the midline on here yet though, so when I want to. So I'm going to average 60 and 40 to find out where the midline is. This one's kind of an easy one to eyeball. Halfway between 60 and 40 is 50. So there's my midline. Okay, next thing I need to do, that's my graph, is I need to write an equation that expresses the distance from the floor, that's my height above the floor, let's call it my height, in terms of the number of seconds the stopwatch reads. So in other words, I'm using my t and my h to write a function. And t is like your x and h is like your y. You could use h and y, x and y if you want to. We could just say h of t, might be the best way to write it as a function. But let's first analyze what we've got here. We need to know the amplitude. That's how we're going to find our A. We need to know the period. That's how we're going to find our B. We need to know the phase shift. And we need to know the vertical shift. And I'm writing off the screen, so let me move that up a little bit. Okay, the amplitude is how far above or below the midline it goes. Well, from 50 to 60 is 10. From 50 to 40 is 10. Amplitude is 10. Amplitude is never negative. If you have a negative in front of it, that indicates a flip or a reflection across that midline. But we don't call that part of the amplitude. That's just a separate thing. Okay, period. We just said it was 3. Now, this is how I find my B. That's not B. This is how I find it. Remember that the period is 2 pi divided by B, or B is 2 pi divided by the period. So in this case, that's 2 pi divided by 3. So B is 2 pi divided by 3. All right, the phase shift, the first time we know what's going on is 0.3 seconds into timing. So that means 0.3 to the right. So 0.3 right. And vertical shift is up to the midline, so that's up to 50. So 50 up. Okay, so it's time to write all of those things as an equation. And that looks like this. First of all, is this flipped up or flipped over or not? Is it upside down? Nope, it's right side up. Starts high. So we've got y equals positive 10 cosine 2 pi over 3. This is the b. And I used a y. I was going to say h of t. Same idea. Sorry. Go that. T minus, is it going to be minus? If it's to the right? Yes, it is. And 50 up. There we go. So I'm going to type this in my calculator, and here's how I'm going to type it in. Y equals 10 cosine, parentheses, parentheses. Now this one, I'm going to go a little crazy. That's not b, sorry, that's 2/3 pi. I'm going to go a little crazy, and because my fraction has a product on top of it, I'm going to even put that in parentheses. 2 pi divided by 3, close parentheses, times t, or x, minus 0.3, and then close parentheses. And this is how I'm going to input it. Lots of parentheses. You may not want to use as many as me, but the good news is you can tell whether or not you've graphed it correctly, whether it's working, in terms of whether or not you get a sinusoidal curve. If you don't put it in correctly, you're going to get something that doesn't go up and down like a sine wave. So you'll see that something is not right with the world. Okay, so here is mine. There we go. Let's go back so if you can see a little bit better. There we go. Okay, so now when I graph it, I may or may not be able to see it well. Very often not, because I need to fix my window. But to fix my window, I need to know where is it I need to look. Well, let's look at this graph again. The y values that I can see here are from 40 to 60. So that's where my y values need to be. So I'm going to say like maybe, oh, I don't know. How about show from 30 to 70 so that I can see all those y values really well. My x values go from 0.3 to 3.3. And depending on what's asked, I might need to see a little bit more of it. So let's look at that. This is find the distance from the floor when the stopwatch reads 17.2 seconds. That means 17.2 on T. So that's way out here. So I'm going to need to show like maybe all the way out to 20 seconds. And 0 is good enough, but I don't want to put it right on 0 because I'd like to be able to see where the 0 is. So I'm going to go from -2 to 20. So that's just me thinking out loud what my window is going to be. So I'm going to go window. So hard to see this when I angle it for you. Let's see. I know it's not the easiest thing for you to see either, so we'll just both muddle through. I'm sorry, I'm putting my y values in my x. My y values go from -2, my x values go from -2 to 20, and y values we said we wanted from 30 to 70. And then I'm going to graph it, and I should be able to see a pretty sine wave. There it is. Okay, now one thing, since I said that, one thing that I haven't mentioned that people who not in our class might not understand about this is, why do I keep using cosine? We decided that we were going to, for all of our application problems, just use cosine because cosine can be easier to write because it's very often that we know what happens at the top like we know when our graph is at the top, or we know when our graph is at the bottom. The top or the bottom is an easy place to spot. The middle is not so easy. Sine waves start at the middle. Cosine waves start at the top and the bottom. So that's why cosine waves can be a little bit easier to handle in terms of figuring out where does it start, where does it stop, etc. So we just decided we'd write them all in terms of cosine. Both of them are sinusoids, meaning basically every sine could be rewritten as a cosine and every cosine could be rewritten as a sine. Basically, you just have to shift it over a little bit. So it really doesn't matter which one you use, except for that it can be convenient to start at the top or bottom, which is where we think of cosine starting or stopping. Okay, so remember to plug in x values. I go to second, trace, 1, and I plug in any x values I need to plug in. In this case, that means t values. So it asks me, predict the distance from the floor when the stopwatch reads 17.2 seconds. So I'm going to type in 17.2. And I get 43.3 for y. So 43.3 centimeters. What was the distance from the floor when you started the stopwatch? Well, when we started the stopwatch, that means t was 0, which is x. So again, I went second, trace, 1, and I can plug in 0 for x. And I get 58.09, or let's call it 58.1 centimeters. Oops, 0.1, sorry, centimeters, 58.1. Predict the first 3 positive values of time at which the weight is 59 centimeters above the floor. So 59 centimeters is a height. 59 centimeters is a height, which means that's a y, so it's like we're plugging in a y. So this is where we go to y equals, and we put a second equation in. And I'm going to put y equals 59. And then I go back to the graph, and I can see the 59 going through the top of the graph. And basically I want to know the first 3 times to the right of the y-axis that the line meets the wave. I'm going to zoom in a little bit so I can see that a little better. I don't need to see all the way over here right now. I can zoom in on just this little area here. So I'm going to go tighten up my x's and y's and say x's I just want to see from -2 to 5, and y's, those were near the top of the graph. So let's go from maybe 50 to 65. So here's my top of my cosine graph or sine graph, and there are those lines. And I want the first 3 positive places, so the first 3 places to the right of the y-axis where these cross. And I'm guessing it does cross once right here close to the y-axis. So here's what I'm going to do. I'm going to say second, trace, intersect. First curve, second curve, there's only 2 curves input in my calculator, so that doesn't matter. I just press enter, enter. And then guess, and I'm going to come way over here where the first one is, where I think the first one is, and put my cursor there before I hit enter. And it says at x is 0.08, y is 59. So yeah, I was right. That is a positive value. That is the first time it crosses. So 0.08 is the first positive value of time. So 0.08 seconds. Then the next one, I go back through the same process. Second, trace, intersect, first curve, yep, second curve, yep. Those are just enter, enter. And then guess, I need to move my cursor to the second place that I'm looking at. And that's at 0.52 seconds. And let's do it again. Where's my cursor? Uh-oh. Start over if something like that happens. And at 3.08 seconds. So I think the next one was 0.51 and then 3.08 or 3.1. So those are the first 3 times. Basically we had and it was saying here's your 59 coming along, first time, second time, third time. That's what we needed to find. And we did. Voila.